Alright, so this ICE has a lot of multiple choice questions on it. Normally I'd try to offer these as, say, clicker questions in class, but for the purpose of this one, I recommend trying to get a chance to look through all of these and try to figure them out on your own first, and then come back to the video and kind of check your answers. If you have questions, as always, feel free to post on the discussion boards. So if you take a minute, pause, give it a try, come back. Alright, I assume you've tried them and have come back. So the first question is true or false. Each vector space has a unique basis. So we saw multiple examples in the notes already where we had, say, R3 or P2, and they had multiple different bases. So unique, of course, has only one. You can think of it like Tigger, if you remember that movie. So here, this is false. And maybe you put that you were not very confident, but you should be super confident. It's definitely false. We definitely can have more than one potential basis for a vector space. Alright, so we want to know which of the following describes a basis for a subspace. So a basis is a linearly independent spanning set for V. So that's true. It needs to be linearly independent. It needs to be a spanning set. So that's true. A basis is a minimal spanning set for V. So that's also true. So remember, we said that we wanted to go ahead and try to make our spanning set that we have as few vectors as possible. And that's what linear independence does for us, is it takes a bigger set of spanning vectors and turns it into a smaller and smaller and smaller and smaller set. So here, B is also true. C says a basis is the largest possible set of linearly independent vectors in V. Once again, that's also true. So if we have a set of linearly independent vectors that we can use to span V, if we add another vector, then it's no longer going to be linearly independent. We'll have too many vectors in there. So it ends up being all of the above. Alright, so let's take a look at 3. So 3 says, which of the following sets of vectors forms a basis for R3? You can manually check each of these in order to try to figure it out, but let's just kind of do a quick dimension check. So remember, the dimension of R3, and we should know this from the notes, is going to be 3. So that means any of these sets that doesn't have 3 vectors cannot form a basis specifically. So remember, basis means that we have to have a specific number of elements, so it can't be 1, it can't be 3, and it can't be 4. So just by process elimination and the choices we have here, it's going to be E. Now I still recommend checking the properties on your own. So, should verify this is a spanning set for R3, and you should verify that the set of vectors is linearly independent. But if you have questions on that as you're trying to do that, I recommend throwing those on the discussion board. Gives you some things to talk about. Or even if you can show that it is and you want to post about that in the discussion board, definitely feel free. Alright, so let's look at the next question. So which of the following sets of vectors spans R3? So we know that 2 will, since in the previous problem it's a basis. So 2 is possible. 1 won't work because it has too few vectors. And that just leaves 3 and 4. If you notice, going from the first vector to the third vector, if we just multiply the first vector by 2, we get this vector. So this is not going to help us span R3 anymore. And if we go from this vector to this vector, we're also multiplying by 2. And so this vector will not be a useful building block if we're trying to span R2. So V won't work, and 4 won't work. And in the end, 3 we could check by taking -2, 1, 3, 6, x, 0, 2, 0, 2, y, 0, 0, -2, -2, z, and getting the reduced row echelon form. And what we'll see is that this ends up being a spanning set as well. So here it ends up being that both C, that both 2 and 3 are going to be spanning sets. So we want to then look at the last question. So which of the following describes the subspace of R3 spanned by the vectors from that last set? So remember, we talked about how these were going to be kind of redundant vectors and not kind of help us in our description. And so if we look here in 3 dimensions, what we have are 2 different vectors and every possible linear combination of those vectors. And so this combined together, it's not going to form a single line. It also won't form all 2 because we do not have things that are just in R2. Remember, R2 is things in the form xy, instead of all xy, such that x and y are in the real numbers. So it won't be R2. It's also not going to be all of R3. So notice that we only have 2 vectors here, and we're not going to be able to get to R3 because we would need 3 linearly independent vectors, and so it ends up being just a plane of some kind.